Have you ever stopped and wondered if a computer can really be creative? I don't just mean spitting out data or following a program. I mean actually generating something totally new. Something that looks like it came from, well, an imagination. That's the huge question we're going to tackle today. Okay, so let's get right into it. We're going to explore this really cool type of AI model called a neural network, which is basically a computer system that learns patterns in a way that's kind of inspired by our own brains. And we're zooming in on a very special kind of network, the Variational Autoencoder, or VAE for short. This is one of the key technologies that lets machines go from just recognizing stuff to actually creating it. So, here's our game plan for this explainer. We're going to start with the big picture. What even is a VAE? Then we'll break down its two main parts, the encoder and the decoder. After that, we'll get into the real secret sauce that makes it all click, the loss function. And finally, we'll see why this stuff is such a big deal. All right, let's start with the basics. What in the world is a variational autoencoder? Well, to really get it, it helps to first look at its simpler cousin, the standard autoencoder, and then see how the VA takes this huge leap forward. Think of a standard autoencoder like a super meticulous librarian. Its main job is just compression, taking a big image and shrinking it down to one single fixed code that holds its most important features. It's all about being efficient. But a VAE? A VAE is more like an artist's sketchbook. Instead of mapping an image to one single code, it maps it to a kind of fuzzy region of possibilities, a probability distribution. And that small change, that's the whole ballgame. It shifts the goal from just compressing to actually being creative. This diagram right here is going to be our guide through this whole thing. Think of it like a data factory. On the left, we feed it an input image, let's call it X. That flows into the first machine, the encoder, which makes a really compact little summary of it we'll call Z. This summary then gets passed to the second machine, the decoder, which uses that little summary as a blueprint to try and rebuild the original image, creating our output, which we'll call X prime. At first, the goal is just to make the output look as much like the input as possible. Okay, so here's the most important part. The whole point of a VAE isn't just to be a really complicated copy machine. Nope. The real magic happens in that middle part, Z, what we call the latent space. The VAE wants to learn a rich, structured map of all the data in this latent space so that later on, we can just pick any random spot on that map and ask the decoder to dream up a totally new image from it. So, how is this map actually created? Let's zoom in on the first half of the system, the encoder. If the whole VAE is a creative agency, the encoder is the mapmaker, the one who looks at all this complex real-world data and draws a simplified, organized map of it all. At its heart, the encoder is a neural network that does something called dimensionality reduction. Now, that sounds super technical, but it's basically like writing a one-page summary of a 1,000-page novel. It takes something with a ton of information, like a simple 28 by 28 pixel image that has 784 different pixel values, and it squishes all 784 of those numbers down into a much, much smaller little code, Z, that might only have, say, 20 or 30 numbers. And this right here, this is the VAE's big plot twist. See, a normal encoder would just spit out that little code, Z. But the VAE encoder is different. It outputs two things, a vector of means, called mu, and a vector of standard deviations, called sigma. These aren't the final code themselves. They are the instructions that describe that fuzzy region, that neighborhood we were talking about earlier. To put it another way, instead of giving a single, precise GPS coordinate for an image on our map, the encoder just gives us a general area. The mean, mu, tells us the center of that area, and the standard deviation, sigma, tells us how spread out it is. It's this little bit of built-in fuzziness that makes all the creativity possible. All right, so our encoder has drawn this probabilistic map. Now what? How do we actually use it to create something? Well, that's where the second half of our system comes in, the generative decoder. You know, the process is actually pretty slick. We use that mean and standard deviation from the encoder to define our neighborhood. Then, and this is the key step, we just randomly pick one single point, Z, from inside that area. It's kind of like throwing a dart at a dartboard to see where it lands. That randomly chosen point is the final code that we hand over to the decoder. And it's the decoder's job to look at that one little point and generate the full detailed image that it represents. The decoder is pretty much the exact opposite of the encoder. It's another neural network that takes that simple, small code, Z, and blows it back up, expanding it into a full-sized, detailed image. It literally predicts the brightness value for every single pixel needed to create an output that, fingers crossed, looks just like the image we started with. Okay, so we've got an encoder making a map and a decoder drawing pictures from it. But that leaves a pretty big question. How does the system learn to do any of this stuff well? How does it even know what a good map or a good drawing is? The answer is in what we call the loss function. You can think of it as the strict teacher that grades a VAE's work and tells it exactly what it needs to fix. All right, I know what you're thinking. This formula looks complicated, but don't let it scare you. The idea behind it is actually a really elegant balancing act between two different goals that are pulling in opposite directions. We're going to break it right down. So, this loss function is basically a tug of war. The first part is the reconstruction loss. This just measures how different the final image is from the original one. This part pushes the VAE to be a really good artist, to make copies that are super accurate. The second part is the regularization loss. This measures how neat and tidy our latent map is. This part pushes the VAE to be a really good librarian, keeping everything organized so there are no empty, weird gaps on our map. That regularization part uses a fancy math tool called Divergence. For our purposes, all you need to know is that it's a way to measure the distance between two probability distributions. With a VAE, we use it to measure how far our little encoded neighborhoods are from a simple, perfect bell curve. This just encourages the encoder to keep those neighborhoods from getting too wild and spread out. So why do we even need this librarian? Why do we need the regularization? Well, without it, the encoder would totally cheat. To get a perfect score on reconstruction, to be the perfect artist, it would just memorize every single input, mapping each image to its own tiny, isolated little dot in the latent space. And yeah, that would make it a great copy machine, but it would be a horrible generator. The space between all those little dots would just be meaningless static. The divergence forces those neighborhoods to overlap, creating a smooth, continuous map of features that you can actually explore. So, we've walked through the encoder, the decoder, and the two-part loss function that teaches them. Let's put it all together and talk about the payoff. Why do we go through all this hassle to build a smooth, organized latent space? And this is it. This is the big payoff. Because that latent space is now a meaningful, continuous map of ideas, we can actually go exploring. We can pick a spot on the map that doesn't belong to any specific input image we showed it, feed that spot to the decoder, and it will generate a plausible, brand new image. It can mix and match ideas. This is how we get from just copying to actually creating. And this just shows the result perfectly. After you train a VAE on thousands of photos of faces, it can start to generate new faces of people who don't exist. It didn't just memorize the faces, it learned the underlying idea of a face, and now it can create endless new versions. That is the power of generation. So, let's do a real quick recap. The magic of a VAE isn't just about shrinking data down. It's about learning a rich, probabilistic map of that data. You've got the encoder, our map maker, that describes these regions of possibility with a mean and a standard deviation. You've got the decoder, our artist, that can take any point on that map and create something new. And the whole thing is trained by a clever two-part loss function that balances being a good artist with being a good librarian. It's that balance that unlocks everything. And then this all leaves us with one last really fascinating question. We've seen that VAEs can learn the idea of a human face and create new ones. But this isn't just for images. Imagine training a VAE on thousands of songs to create new music. Or training one on molecular structures to design new medicines. What happens when our creative partners aren't just other humans, but algorithms that can explore possibilities we haven't even thought of yet?